In this series, we will look at Generative Adversarial Networks, shortly GAN. The GAN is a neural network-based generative model. The variational autoencoder, shortly VAE, we looked at in the last video, is a type of generative model consisting of an encoder and a decoder. The GAN is also a type of generative model consisting of a discriminator and a generator. The VAE is a probabilistic generative model, and the GAN is a model in which a discriminator and a generator learn through competition with each other. In this video, we will look at the architecture of the standard GAN. This video was produced in Korean and translated into English. My voice is generated by AI, text-to-speech. Let's look at the full table of contents. In Chapter 1, we will look at the standard GAN. We will look at the basic concepts of GAN, loss function, and learning algorithm. And let's implement a GAN model that generates two-dimensional data consisting of multiple clusters. Finally, let's look at the problems of the standard GAN, such as mode collapse. To address these issues, various GAN variants have been developed. From Chapter 2 onwards, we will look at some of the variants of GAN and implement them one by one. In Chapter 2, we will look at the DC GAN, which is composed of convolutional neural networks. We will implement a DC GAN model to generate NIST images. In Chapter 3, we will look at the unrolled GAN introduced by Luke Metz et al. In 2016. In Chapter 4, we will look at the least squares GAN proposed by Shudong Mao et al. In 2016. In Chapter 5, we will look at the Wasserstein GAN introduced by Martin Arjovsky et al. In 2017. In Chapter 6, we will look at the WANGP proposed by Ishan Gulrajani et al. In the paper Improved Training of Wasserstein GANs in 2017. In Chapter 7, we will look at D2 GAN, proposed by Tu Ding Nguyen et al. In their 2017 paper, Dual Discriminator Generative Adversarial Nets. The GAN was first introduced by Ian Goodfellow et al. In their 2014 paper titled Generative Adversarial Nets. In this paper, they propose a new framework for estimating generative models via an adversarial process, in which they simultaneously train two models. One is a generative model G that captures the data distribution, and the other is a discriminative model D that estimates the probability that a sample came from the training data rather than G. This framework corresponds to a min-max two-player game. This model can be trained via the following algorithm 1, presented in the paper. In this video, we will analyze this algorithm in detail. And we will use this algorithm to implement a GAN model. The GAN consists of two neural networks, a generator and a discriminator. The generator takes random noise as input and generates fake data that is as close as possible to the real data. The discriminator receives fake data generated by the generator or real data as input and distinguishes whether the input is real or fake. The discriminator uses a sigmoid activation function to output values between 0 and 1. When real data is input, the discriminator outputs a value closer to 1. And when fake data is input, the discriminator outputs a value closer to 0. If the GAN model is well trained, the discriminator tries to distinguish between real data and fake data. and the generator can produce fake data that is so similar to real data that the discriminator cannot distinguish between them. The discriminator and generator are in competition with each other and gradually reach a Nash equilibrium as the model is trained. When in equilibrium, the discriminator outputs 0.5 when real data is input, and also outputs 0.5 when fake data is input. That is, the fake data becomes so similar to the real data that the discriminator cannot distinguish between the two. As a result, the generator can produce fake data that is very similar to real data. After training is complete, you can use the generator to produce an infinite amount of fake data that looks similar to real data. Next, let's look at the loss function for GAN training. Training a GAN requires two objective functions, one for training the discriminator and one for training the generator. The two objectives work together. First, let's define the notations used in the GAN model. Let D be a discriminator and G be a generator. And let's call the parameter set of D theta D and the parameter set of G theta G. When X is input to D, let D of X be the output of the discriminator. And when Z is input to G, let G of Z be the output of the generator. When G of Z is input to D, let D of GZ be the output of the discriminator. Let X be the real data from the distribution of P data of X. And let Z be the random noise coming from some distribution PZ, such as a uniform distribution or a normal distribution. And let V of D and G be the loss function for training a GAN model. We'll look at this loss function in more detail later. The first E represents the expectation for samples X from the P data distribution, and the second E stands for the expectation for samples Z from the PZ distribution. The discriminator tries to maximize the V of D and G by making D of X equal to 1 and D of GZ equal to 0. That is, when real data X is input, the discriminator updates theta D so that the output D of X has a value close to 1. And when fake data G of Z is input, it updates theta D so that the output D of GZ has a value close to 0. The generator tries to minimize V of D and G by making D of GZ equal to 1. That is, when fake data G of Z is input to the discriminator, the generator updates theta G so that the output D of GZ of the discriminator has a value close to 1. The generator does not directly affect the log D of X term in the V of D and G. Once training is complete, the generator receives random noise Z and generates G of Z that resembles real data. The discriminator cannot tell whether the input X or G of Z is real or fake. That is, both D of X and D of GZ are 0.5. This means that D of X is identical to D of GZ. As a result, the generator can successfully generate fake data that is very similar to real data. Therefore, the min-max objective function for GAN training can be written as follows. Now that we know about the loss function of GAN, we can easily understand algorithm 1 presented in the paper. This algorithm alternately updates the network parameters of the discriminator and generator. Sample mini-batch of M noise samples Z from noise prior PZ. Sample mini batch of M examples X from data distribution P data. Then we update the discriminator by ascending its stochastic gradient. The discriminator tries to maximize V of D and G. The gradient of the average of V with respect to theta D is as follows. Update theta D by gradient ascending. This process is repeated k times. That is, theta D is updated k times, where k is a hyperparameter. The authors of the paper used k equal to 1, the least expensive option, in their experiments. Next, we update theta G once using gradient descent. Since the first term of the loss function is independent of G, we use the gradient of the second term. Minimizing this term is equivalent to maximizing this term. The gradient is larger early in learning when you maximize this function than when you minimize this function. Therefore, using this objective function, theta G is updated faster in the early stages of training. The gradient-based updates can use any standard gradient-based optimization algorithms, such as Momentum, Attograd, and Atom. Next, let's look at how the distribution of fake data generated by the generator and the distribution of real data change as D and G are updated. The distribution of real data X is P data, and it looks like this. The distribution of random noise Z is PZ, and in this example, it is uniform. The output of the generator is G of Z. The distribution of fake data from G of Z is PG, and it looks like this. A is an initial state. Let's assume that PG is somewhat similar to P data, and D is a partially accurate classifier in this state. At state B, D is updated k times in the inner loop of algorithm 1 to converge to D star of X. We will look at this formula in more detail on the next page. When X from P data is input to the discriminator, D star of X becomes 1. And when X from PG is input to the discriminator, D star of X becomes 0. When X from the overlapping part of the two distributions is input to the discriminator, D star of X will have a value between 0 and 1. In this case, the discriminator cannot accurately distinguish whether X is real or fake. In state C, G is updated once. PG and P data become more similar in this state. The two distributions overlap a lot. In state D, B and C are repeated multiple times. After the iteration has completed, the distributions of PG and P data match well. And both D star of X and D star of GZ become 0.5. That is, the discriminator cannot distinguish between G of Z generated by the generator and real data X, which means that G of Z is very similar to X. In this equation, if PG and P data are equal, D star of X is 0.5. Next, let's analyze this loss function mathematically in more detail. In the paper, this equation is expressed as follows. It is said that the second term of this equation can be written as follows by the Radon-Nikodym theorem of measure theory. Let's understand this intuitively. The second term of this equation is obtained by inputting Z from PZ into G, inputting G of Z into D, and calculating the average with D of GZ. The second term of this equation is obtained by inputting the x from Pg into D and then calculating the average with D of x. The two expectations are equal. Using the integral symbol, we express the expectation as follows. Fixing g and differentiating this equation with respect to d of x, we get the following. Then the optimal discriminator d is as follows. Next, we substitute d star into the original loss function to find the optimal g. To simplify notation, let d be p data and g be pg. Then, this equation can be written as follows. And rearranging this equation gives us the following equations. Since both the integral d dx and the integral g dx are 1, the first and second terms are each negative log 2. Therefore, this equation can be written as follows. The second and third terms are KL divergence, respectively. And the two KL divergences can be expressed as Jensen-Shannon divergence. The more similar the distributions D and G are, the smaller the JSD will be. If D and G are exactly equal, this term is 0. Minimizing V star is equivalent to minimizing the JSD of P data and PG. If P data and PG are equal, V star converges to negative log 4, i.e. negative 1.3863. Therefore, as the GAN model learns better, the loss V converges to negative 1.3863. So far, we have looked at the basic architecture of a GAN and analyzed the loss function. In the next video, we will implement a GAN model to generate two-dimensional data consisting of multiple clusters.